Welcome to Journeys in Jupyter 201, Cleaning Data. If you haven't already set up your environment, take a look at the 001 Jupyter Notebook setup that's listed on the YouTube site as well. And if you've got everything ready, your Anaconda installed, and you've got your tutorials unzipped, go ahead and hit the Anaconda folder and Jupyter Notebook. You'll get a console window that'll come up, and then you're going to want to navigate to the desktop and then on to cleaning data, and then finally on to introduction. So again, this is cleaning data in Pandas. It's tested on Anaconda 3, and I'm Theo Nonheim. So check out the hyperlinks as we go through. Most of the hyperlinks, especially the ones on the bottom of the page, will go straight to documentation or other tutorials that are better than this one. So I highly encourage you to take a look at those. In addition, we're doing this in Jupyter Notebook format. Escape H will bring up your help window for the user interface. You can press Shift Enter or Control Enter to run a particular cell as we go through. So our goals for this session are to provide a high-level overview of the Pandas library and conduct specific tasks related to loading data, removing and or compensating for missing data, cleaning data for specific data types such as numeric data, string data, time series data, doing complex transformations and other useful techniques. So moving on, go ahead and click on Loading and Exploring, move it up in a new tab. And I'm going to go ahead and close the introduction because we no longer need it. And so we're moving on to loading and exploring. So in a general sense, like most things, if you can do it right the first time, it's a lot easier that way as opposed to having to come back and fix the data and munge it later on. So what we're learning here is data wrangling or data munging. In other words, we're going to learn how to fix data that's bad so we can process it and go ahead with our day. So we've got support for a large number of input types, but we're going to mostly be working with read CSV, read Excel, and various data frame construction methods. So here's a list of the libraries we're going to be dealing with, along with the documentation to go to those libraries and read through. First, I'm going to import our libraries, and then I'm going to quickly go to the data types, if it would load. And then we're going to start with the wild, wacky, and wonderful world of file types. So a lot of times you'll have fixed with files. For example, if you're getting output from a mainframe or you're getting an output from a batch process, you'll often use fixed with files. And then so we've got CSVs, JSON, HTML, so like a table from the internet, Excel, some big data formats, Stata, and then SQL as well. So feel free to take a look at those. We're going to start with fixed with data files. So as you may be aware, fixed with data files are really just simple text files. They'll have 10 or so characters devoted to this column, 15 to the next column, etc., etc., etc. And so we can open those using the read fixed with file format. The fixed with format method, which basically just takes the path to your data set. It can infer the columns, or alternatively, you can input your columns as necessary and say that the individual columns are at the 10-digit mark, the 20-character mark, etc. And it'll put it into a nice data frame like this that you can use. A lot of times you get really messed up CSVs. I'm going to just run this one. For example, this one has semicolons instead of commas separating the CSV elements. So we just say we want a separator of a semicolon, and we will get a nice data frame out of that. So we just put in the path and we add this optional separator argument, and so we take this text here and we transform it into the data frame. For the sake of demonstration, I've added a bunch of optional items. So you can add a title to the index column. You can only use a subset of the columns if you want. You can transform the data as it comes in if need be. You can format things. You can supply custom null values. You can change the encoding. And then you can skip bad lines if you want. Read CSV is also excellent. It's got a variety of arguments you can use. I highly encourage you to read the documentation because it's impossible to keep this all in your head. Read Excel. I don't like Excel personally. You should use CSV files if you can, but if you need to use Excel files, Pandas has facilities for that. This is the, and just as a brief side note, going to the desktop, going to cleaning data, going to data. All the data for this presentation is going to be inside this data folder. For example, the Greenway analysis folder Excel we're using right now is in this folder, and we're just opening it. As you can see, it's Excel files are filled with binary data, so this is basically just binary data, and Excel gets translated into a data frame via the read Excel, and you just supply the path and any optional arguments you want to put on that as well. The read Excel signature, because it's less flexible, there's less things to do with it, but you can supply things as needed. One quick note, if you take a CSV file like this CSV file here and you try to read it as an Excel, you will confuse your interpreter. It will not know what to do. Similarly, if you supply a Excel file, a binary Excel file to a read CSV file, to the read CSV method rather, it will not know what to do. So just remember, only supply the types of data that are acceptable for your particular function. So if you have JSON, use the read JSON format function. If you have HTML, use read HTML. And just as a side note, you can also build data frames from scratch with raw data using dictionaries, records, items, etc. This is the simplest method. So for example, I'm going to create a data frame using a dictionary like this, and the keys, number, message, are going to be our columns, and then the data that you supply can be whatever you want. So in this case, we're supplying 3 random numbers based on a normal distribution, and we're also just adding 3 different words. You can also, if necessary, add an index if you want. So as you can see, we've generated new numbers and now we have a new index. So one important thing to pay attention to, character encoding. Back in the day, you didn't have to worry about character encoding because everything was in ASCII. But nowadays, you have to change character encoding at times, and you can just think of character encoding as the manner in which you translate bytes to characters. So just think about it as the way that strings are comprised on a disk. So some of the things that you'll see are CP1252, which is the Windows code point, UTF-8, which is the lingua franca of the internet, it'll be everywhere, ASCII, which is old but good. It is actually a subset, or rather UTF-8 is a superset of ASCII, and then Latin 1, which you need to be wary of because Latin 1 will never fail. You can put any encoding into Latin 1 and it'll come out with at least a guess at what it wants. A list of encodings are listed on the Python page, which you're free to take a look at. There are a bunch of them, so I'm not going to go into all of them, but here are some of the standard encodings. So default is UTF-8, which is a sane default. Here we have a set of entries that basically have this smiley face, which is a UTF-8 character, but you won't find it in ASCII, for example. We can try to read this UTF-8 file with a CP1252 code point, but it just scrambles a bunch of stuff because it's not translating the bytes in the correct manner. And then sometimes, if you try to put a Unicode string into an ASCII interpreter, it will not, every ASCII character has to be between 1 and 128. This particular character is not between 128 and 256, I'm sorry, between 0 and 128, and therefore it won't work. So remember that ASCII will fail if you put in non-ASCII characters. How do we determine encodings? So there is a there's a package called Cardet or Chardet. basically a character determination package. And so what we're doing here is you basically read any file, you get the binary data, and you feed it into this char.detect function, and it'll give you the encoding. So we can get the encoding, we can get the confidence, and for example, we just went through all the files in the folder and we pulled them out and we said all the CSVs, we want to find out the encoding and we want to find out what the confidence level is for that. So for example, the 1252 table was correctly predicted as 1252 with 73% confidence. The ASCII table was predicted as ASCII with 100% confidence, and we go down the list. In addition, you're going to run across badly mangled CSV files. There's no two ways about it. And so we're going to go through some of the common scenarios for dealing with malformed data that isn't specific to a type. So if your whole data set is messed up, these are some of the functions you would use. So one of the common things that you'll see is data without headers. As you'll see, this is information about wildlife refuges, but there's no information about what they are. It just starts with the first column, which is actually data and not a header. So if we want to pass information about a header, we simply list our columns and then we say header none, there is no header, and then the names we want to use is this list right here. So we just supply the names we want. You can alternatively use this format here, but it's not quite as good in my opinion. So we've instead of having this data listed in the header, we now have a proper header and we have the data listed below as we need. In addition, a lot of times you'll get bad feeds where people will give you duplicate data, which can be quite annoying. This is easily handled in Pandas just because it's a common thing that comes up. So for example, we have this wildlife refuge data. We're basically just drilling down. We only want the complex name is equal to Devil's Lake. And then so we can see that we have some duplicates here. And so how do we drop duplicates? We have this nice simple drop duplicates function. And then here, for example, we are dropping the exact duplicates. So as you can see, this is a duplicate with that, so it got dropped. This was not a duplicate, so it did not get dropped, and then it goes on. And this is actually giving us the entire data set. We're just drilling down to the top three. There's it's 150 rows long or more. So if we want to be a little bit more complicated than that, for example, we don't want the exact duplicates, but we want any duplicate where complex name and organization name is the same, we want to drop it, and we want to keep everything else. So we can drill down into these two columns and leave everything else untouched. We're basing our duplicates solely on these two columns. In addition, we can just not read the data we don't want. In this example, we only want the ID, complex name, and organization name, so we say we want to use calls and then these three columns, and so we don't need to bother with all the extra data. In addition, sometimes you get garbage, and there's no two ways about it. In this example, we're taking our old weather stuff, and as you can see, we've got a smiley face, which is a Unicode symbol, and if we were to say that particular character is junk, we don't want it, we can go to replace, and then we just replace that smiley character with these three characters, period, underscore, period, and make it a frowny face. So as you can see, we've replaced this bad character and put in these three good characters in its place. A quick idiom that you may want to use is if you want to find any particular garbage character, you can just say, I want where the data frame is equal to this particular character. And so it'll give you a frame that says true, false, true, true, true. And then you can just get any, axis 1, and you'll be able to pull out any particular row that matches this pattern. So like that. In addition, Python's generally pretty efficient when it comes to packing a lot of strings or numbers into space. That said, if you need to chunk stuff out, you can do that. This particular this will go through the data frame in chunks of 100 and let you process that chunk individually. So this basically just says the first cell in chunk 1 is a dare, and it goes all the way through. And this is, if we wanted to process it, this is an example of this is the head of the fourth chunk. So the fourth chunk starts with Pulaski, and it's got this information. You've also got the ability to do offsets. So if I want to skip 300 rows and then read 100 rows, I can do that using this simple keyword combination here. Out of core, you can use third-party libraries like Dask for lazy evaluation, or you can just cache stuff to disk or use key ranges as needed. In addition, you're going to probably need to explore data, so this is some of the high-level things that you can do. If you want to find, so I want to find all the unique names in this main Greenway column, and so I store it to Greenway names. And then I want to iterate through those Greenway names and find anything where path is in that name. So basically, I want to find where where path is in this main Greenway column. I would get these 7 separate items. And you could also just do, if you wanted to see the Greenway names, just as easily you could do that if you didn't want to filter them down. You can also get the data types. As you can see, we've got an integer, a float, and then objects are always pretty much strings in Python. So any Python object or string will be an object in this. You can describe the data set as a whole, which will go through each column, give you the count, the mean, the standard deviation, min, max, and then your quartiles. You can get median. I mean, if you just go to data frame, period, and autocomplete, there is just a ton of different stuff you can do, and I won't get into all of it, but just know that it's there, and you can check the Pandas documentation for that. In addition, you can just drill down to an individual column, and you can check information as needed for the number of null objects and things of that nature. One of the other things that is worth noting, value counts is super helpful. So you can see we've got a lot of Lewis Stevens, and we want to find out how many Lewis Stevens do we have, how many Morris branches do we have. You can use the value counts, and then we've got 1200 Black Creek Crabtree, and you can do whatever you want with that. We can just get the head, and let's multiply it by 1 billion there. I mean, you can just treat it like regular data, which is nice. And then you can also just get the correlation of, for example, this is the iris data set, and we want to get sepal width versus sepal length. And that's an easy way to just pick out correlations between different variables. So 10 Minutes to Pandas is excellent. The Pandas Cookbook is quite good, and then the Pandas Intro to Data Structures is excellent. I highly recommend all of those items, and I'm going to close this and move on to missing data. Missing data. Unfortunately, you cannot avoid missing data. You're going to run into it everywhere, and consequently, we've got good resources for dealing with it. Before we get to that, though, I want to briefly take a detour onto null and none and nan. So not all null values or missing data values are alike. For example, we have null, which is SQL or structured query languages item or class that specifies the absence of a value. It's not 0, it's not an empty string, it's just basically missing data. You'll get that mainly out of databases, relational database management systems, and it'll be converted to something like a nan or a none before you work on it generally, but not always. None is Python's native missing data type, so you can assign it like a variable or anything else. It's not false. False is not true. None is we don't have information on it. So none, it can be in data frames, but it's generally not as good as nan. Nan, or not a number, is a NumPy data type, often seen as npnan, and it's weird by design. It's built into the ISO standard for for floating point values, actually, and that allows you to do some pretty quick stuff, and it's super efficient. And so just remember that it's technically a float. And also remember, if you're comparing something to nan, you need a specialized value to do so. So NumPy nan is not equal to NumPy nan. It will give you false. If you compare anything to NumPy nan, it will give you false. Also related to nan is not a time. So we'll deal with that in a bit. So importing our libraries, Read says CSV allows you to load your nans on import. So these are the default values for nan. Pandas will automatically put numpy not a number for those strings there, and then empty strings. So you can also add your own custom null values. So here is custom null value, and we want to replace that with nan, and so we just say NA values are for custom null values, and we put in our own NAN values instead of custom null values, and then we've got not a time and the zero length strings that come into that as well. In addition, we've got so one of the nice things about Pandas is that it has support for these not a number values. We can easily just drop every row that has a not a number value because it's screwing up our calculations. And then we can also do that on a column by column basis. So here is our state code, and we can just drop NA, and now we've only got 5 state codes. In addition, you can subset this. So if I want to only drop the rows that have a population of 18 to 64 that are not a number, in other words, I only want to drop the NaN values that are in this column, so I would just drop this the third indexed item. We can get rid of that by dropping on a subset for this particular column. Similarly, we can do that for multiple columns. So if we wanted to do it for update date and state code, we could do that. And so you'll see that our update and state code have no null values in them anymore. In addition, we can fill the NA if we want to with a different value, an imputed value if need be. So filling NA with 0 is sometimes a good way to go. This is an example, but it can be arbitrary. You can fill it with a string like unknown, or you can fill it with a date like not a time. So here we filled the null value with unknown and not a time. You can, if you're doing machine learning, a lot of times it's better to fill it with a median value or something like that, so it doesn't mess up the rest of your data set, and it also doesn't screw up your machine learning algorithms. Here the median value, medium val, is ends in 799, and you can see that the this was a null value that now ends in 799. So we filled that null value or NaN value with the median value instead. We can also do forward fill. So if we had Alabama null, 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 and we wanted to fill that all the way down, we just use the forward fill method. And if we wanted to do Florida, Florida, Florida going up, we would use the forward fill method. So we did backfill, forward fill. And then for comparison, you remember you have to use is null or not null because we don't directly compare with NumPy NaN values. So here's a couple of state codes. If you wanted to, if you basically looked at this and said which of these items are null, this is not null, so false. This is false. Null, false. Null, true. Null, true. Null, true, and then back to null, false again. And what that allows us to do is to simply use that mask to filter out everything we want or don't want. So we want the rows with NA in the state code. Here we go. We've got all the states with NaN. If we want to do the opposite of it, it's not null. So we get that mask, run the mask in, and so all the state codes are now good. And again, as you can see, the inverse of null is not null. So you can just invert that if you want, and you can get the same thing. You can also use NumPy NaN as a placeholder. Here we create a data frame, and we just put NumPy NaN in this Y column, and we can just fill that in as need be. So we replace NaN with I am less than 30 for the items that are less than 30. For the items that are greater than 30, we'd basically just say item is greater than 30. Pandas missing data tutorial goes into this in excruciating detail, and I recommend it if you want to actually learn about doing this in a more effective manner. It's pretty long, but it's well worth the time. So on to some data type specific techniques. And I'm going to go and close missing data. And this is where you get the best bang for your buck, really. So data type specific cleaning will make your life much, much easier. So I'm going to start with the string and the string namespace methods. So if a column in a, I'm going to load the data first. So if a column in Pandas is a string, say for example surname, it will have this string namespace attached to it, which means you can access all these awesome methods. I think I'm going to have to assign that to a variable first. So you can access all these cool methods that would allow you to do string functions on each and every one of the items in that column at the same time. So and so going through, here we're going to load a bunch of mangled data, and we're going to try out some of these string specific methods, and we're erroring bad lines false, so we're just going to skip the bad lines for now. So if we want to convert these, as you can see, pure numeric, we import it as a float, but if we want to convert this to a string, we do as type string. That's the most primitive method we can use to transform one data type into another. It's generally good enough for strings. As we mentioned before, we can access the string methods, and for example, here we have replaced the surname column with the uppercase surname. So we basically just capitalized everything in the surname column by going to the string method, the string namespace, and accessing the upper method. There's also additionally a replace method, which is excellent, and if you want to strip white space, string strip. And as you notice, this string replace is returning a series, so we need to invoke the string namespace again. So string replace, and then we're taking the result, string replace, and we're taking the result, string strip. So here we are replacing the tabs with empty space, we are replacing the dashes with a space, and then we're stripping the extra white space. So we got rid of the tabs, we got rid of the dashes, and now we just have alphanumerics in there. We also have the ability to do contains, which is a simple thing. So basically, does this contain king? Does this contain king? Etc. So as you can see, the only one that contains king is Burger King, and so we can use that to index and get the Burger King row if we want and transform it further. As you know, in Python, you can use a string ABCD, and you can use it to subscripting to index it, get the first element, get the second element. We can do the same thing for each of these at the same time. So if I want the first three elements, it's tab something, BUR for Burger King, space RO for rooster, etc. And you can do this. I mean, it's just the same thing as string indexing. In addition, you can also concatenate the columns together. So as you may remember, here what we're doing, we're taking the forename and we're basically just putting it all together. So all the forenames together are Horatio, the Cornelius, Sonny, Loch Ness. Horatio, the Cornelius, Sonny, Loch Ness. In addition, as you know, in Pandas, you can basically take a column and add stuff to it. And you can add two columns to each other, for example. So here we're basically taking the prefix, the forename, and we're saying prefix forename is my name. And so we go all the way down. Captain Horatio is my name. His Highness is my name. Mr. Cornelius, Mr. Sonny, Miss Loch Ness is my name. And I'm going to pull this up one more time. So looking at this, we're going to split a string. So if we want to take this birthday string and we want to split it into 3 different elements, because we have month, day, year, and we want to split it into 3 different elements, we just say string split on the slash, and then we get the results. So we get 5/6/1945 is now a list of 5, 6, and 1945. This doesn't have a slash in it, so it confuses the hell out of our algorithm. 5/10/2015 is 5/10/2015 and all the way down. And you can not only split them out, you can get the first element of that split list using string get and then the item you want to get. So if we want to get the first item, 0, junk, 5, 9, junk. And finally, partition method is really good. If you're not familiar with the partition method, you basically just say ABC partition B. And what it'll give you is, and let me actually give, let's say partition C. So it'll basically say, I want to split on C. So I'm going to put C in one variable, everything before C in a variable, and then everything after C in a variable. And so we get A, B, C, and D, E. And we can use that to split out based on these slashes again and put it into a data frame. So there we go. We take 5/6/1945. Before the slash is 5. The slash is obviously the slash, and everything after the slash is 1945. And when you do this expand option, it'll put it in a data frame instead of compacting it into the list. So it'll take a single dimension and it'll expand it to 3 more dimensions for you to use. In addition, there is the regex extract all. So if you, let me put that up. So basic df. So as you can see, there are social security numbers in some of these biographies. If we wanted to find out what the social security numbers are, we could use a regex expression. So 3 digits, optional dash, 2 digits, optional dash, 4 digits, and then basically a word. So spaces surrounding it. So we can get that Cornelius the Rooster is 333, which is correct. Loch Ness Monster is 555. And you can't see it here, but it looks like Captain Crunch is 1 and Burger King is 2. You can also just replace those instead of extracting them. And here we replace, you can see up here, social, social. We have social redaction. Social redaction, we just put our regex expression in the first element and what we want to replace it with in the second element. And then again, this is the unaltered data frame for comparisons. Finally, the one thing I want to point attention to is the dummies option, which is great for binarizing features. So for example, who pulls rank? Captain Crunch does, Burger King does, no one else does. Who flies? Rooster does, Cuckoo Bird does, no one else does. And then Cuckoo Bird is also cuckoo for Cocoa Puffs, and he flies. So if I wanted to make a new column for pulls rank, so you would have Captain Crunch and Burger King would be true, and then everyone else would be false, we can use this get dummies method. So it'll split based on this pipe character or whatever you want to, you can make it whatever you want. And then it'll build out a little matrix for you. So for example, Horatio pulls rank, Burger King pulls rank, no one else pulls rank. Who flies? Not Horatio, not Burger King. Cornelius does, and the Rooster does as well. And then only Sonny the Rooster is cuckoo for Cocoa Puffs, or Sonny the Cuckoo Bird is cuckoo for Cocoa Puffs. And then finally, there are a ton of numeric methods we can use. So we're first going to use the toNumeric method. So in if you want to convert a string to a number, there are a lot of things that can go wrong. So when things go wrong, we can decide what we want to do with those. So if we want to take the errors and ignore the errors and just put in the string, we can do that. If we want to coerce to nan, we can do that. So for example, if we wanted to coerce this, if we wanted to do height on this column, obviously 12, the number system doesn't know how to deal with that because it's basically just a number. We can say leave it as 12 or turn it into not a number. And so if we wanted to ignore it, we would leave it as the string 12, and if we wanted to coerce, it would be not a number. So here is an example of toNumeric with the ignore option and toNumeric with the coerce option. As you can see, so 999 is a number, it works. 75 is a number, it works. 12 does not work, so the ignore column leaves it be. The coerce converts it to nan. Again, 12 gets left as 12 and then gets converted to nan by the coerce. Now you'll probably be wondering, why is this an integer and why is that a float value? Why do I have a .0 at the end of it? And that's because nan is a float. So if we want to put a nan in a column, that column either has to be a string column, a float column, or a datetime column. So those are the only columns that can contain nan properly. And then sometimes you need to take out characters first. So this is, if you look at this table, how do we convert these to actual numbers? And if you're not familiar, in accounting, if you have a parenthesis around your number, that's a negative number. Just makes it stand out more. So here we are converting the open parenthesis to a negative mark, so so Python knows how to deal with it. We're getting rid of the dollar, we're getting rid of spaces, we're getting rid of the close parens, and then we just translate that and we get the output. And so we clean the float and then we can convert it to numeric, and so we take this amount is now translated to a float. It was originally a string in dollars. This was originally a negative string in dollars, and now it's a float. And then if you want to ever round to something, just use the round method. It'll get, because a lot of times your floats will be like 6 blah 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 blah, and so you want to just convert. You want to round it down to. Yeah, so I would have to assign that first, but that would be how I would round it. Let's see. Oh, clip, another useful feature. So if you have a range of data, but you don't want it to go above or below it, so if you want to get rid of negative values for something, you can clip at 0. If you want to make sure nothing goes above 100, you can clip at 100. And if you can clip at 2 different levels. So if I want to make sure all of my values are between 0 and 100, I would use both clip. I would use clip like that. So let's just go through this. So if we have 99999, huge number, if you add a lower clip, it doesn't matter because it's not below 0, so it's not going to get clipped. But if it's above, if you're going to clip it at 100, it's going to get transformed to 100. And both clip will make sure it's not below 0 or above 100. 75 doesn't get clipped at all because it falls within all of these ranges. Nan is a nan all the way through, so it can't be clipped. In negative 100, the lower clip is at 0 because it's not allowed to be less than 0. So we clip at 0, and then the upper clip doesn't matter to it. But both clip will make sure that it gets at 0 again. In addition, you can also bin things. So if you want to convert these continuous variables to a categorical variable. So, for example, if I have, let's see, if I have 0.5, 1, 0.8, 0.3, 0.2, and I want to convert them to categories, I can do that. So this would be 4 to 5, 9 to 1, etc. And then you can also do that for, you can do this, you can name the bins. So 4 to 5 would be F, or I'm sorry, 0 to 60, 60% would be F. 1 would be an A. Basically, this would be F, D, C, B, and A. So everything between 85 and 100 would be an A. And so, as you can see, we've properly cut that. There's also great support for datetime methods. Like string methods, there's a huge number of datetime methods you can use, and they have a special namespace to access their functions. So again, if we were to go to, well, first we would have to, I'll get to that in a second. So these are some of the datetime methods you can use. If you want to take this birthday and convert it to an actual date that we can do cool stuff with, we can do that. So again, we have the errors ignore, errors coerce. If it doesn't fit, like for example, the 5th day of June, it's hard for our Python interpreter to know how to convert that to a time, we can coerce it. And if we ignore it, we just leave it be. Generally, you'll find that coerce is better. But if we absolutely have to use the 5th dayth of June, we can put together a format string, and we can see that the 5th dayth of June in 1800 is 1800-6-5. But obviously, it will fail for everything else because everything else doesn't meet that criterion. Why do we even care about putting those into Python date objects? Because you can do all kinds of cool, fancy date stuff with it. So if I want to find the day of the week, I can find out that the 5th of June in 1800 was a Thursday. There were 30 days in that month. It was the 3rd day of the week. It's the year, the month, the day, etc. You can do whatever you want with that. This is when you make these format strings, this is the directives that you would use. So you can see that I'm putting in these special characters, and this is how it converts it. Every time I have to do a custom function, I have to look this up. So keep a link to this. You'll never remember all of it. And this is a toy example of how you would use these to convert a bunch of Spanish days. I'm sorry. So this is a function for converting Spanish strings to actual dates. So enero 5, agosto 20, 2015. We use this function using where's the string pattern? Oh well. I don't remember how I did this, but this is how you would translate that. And it translates agosto 20, 2015 to the 20th of August, 2015. If you get lots of data you don't want, so if you have a birthday and you want to make it a day instead of a date time, you can just normalize it. And then you can use these periods in Pandas as well, which are also useful. So if you want a day, you can convert it to a day period. You can convert it to the month period. You can convert it to the 2nd quarter of 1945. You can convert it to the week of 4/30 to 5/6 from Monday to Monday for that year if you want. And then you can, again, output strings as needed. So if we wanted to use our silly date time format from before, we wanted to convert these, we can convert it to the 6th dayth of May in the year of 1945. Working with text data, working with time series. This is where you want to go if you are just getting started with time data or time series data. If you're looking for fancy stuff, rolling windows, things of that nature, you can look at the computational tools here. Offset aliases, if you want to do like business day calendars and stuff like that, you can do it. And then I've added the stirp time and stirf time behavior if you want it. Text data, time series data, and then moving on to other. I'm going to go back and close the date time specific techniques because we're done with that, and we're going on to other. So other stuff you can do, just general bric-a-brac that I think you can probably use when cleaning data. So strategies for dealing with big data. And I need to import my libraries first. That would be helpful. Strategies for dealing with big data. If you convert your strings, if you're using, what's this, names. So if you're using, we have, let's see, value counts. Here, we've got 3 strings and we use them 50 times. Do we want to store all the string data each time? Probably not. We can convert it to what's called a category or a categorical, which is akin to a factor in R. The R statistics programming language, it's called a factor. And we can save a lot of space, and strings will use 4 times as much space as a categorical in this particular example. Again, we can do a chunked read, so if we want to iterate through the table, process it a little bit at a time, and then do something with the result, we can do that. We can also use the CSV module to do a chunked read of sorts. And then finally, Dask. Dask will allow you to delay your computations and do it out of core so you don't have to fit the entire thing into memory. One of the few weaknesses of Pandas, well, let's say it's one of the weaknesses of Pandas, is that huge sets of data have to fit into RAM. Usually you can fit them into RAM, but if you are analyzing all the data on the internet, you would have to defer computation until later. Dask would allow you to do that. In addition, other pre-processing functions, cumulative sum is pretty useful, so it'll go down, add up as it goes. So 5 plus 4.9 is 10, plus 4.7 is 14.7, plus 4.6 is 19.3, and it'll add it up as it goes. You can get the difference in percent change as you go down. So the difference from 4.9 to 5.1 is 0.2, percent change, etc. Go all the way down. Transposing stuff, not easy in SQL, but it's easy to do in Pandas, which you can do like that. You can rank your items with a percentage rank. You can shift columns back and forth. So if you want to compare an observation with 3 observations ago, you can just basically shift the entire series up 3 or down 3. So this is what we're doing. We're shifting positive or negative. So we can do a negative shift of 3. And we will go the other way. So you can compare 3 observations ago to the current observation and go that way. Put that back. In addition, you can concatenate tables together. For example, we're taking A, B, A, and C, and we're just adding these all together. So obviously, C, the data isn't complete because we don't have a lot. We have, let's see, C1. Yeah, so you can just basically stack the data together however you want. The merge tool is great for that. And then in addition, we can change formatted strings before export if we want. So that's just basically how you would do string formatting. And then some useful NumPy functions. So let's see. Oh, this is NumPy where, which is a really versatile tool. So if you want to get the indices where a particular condition is met, you can get that. Here we get the indices and columns for a particular thing, and then we're just going through the list. So sample 33 is equal to 55 in column sepal width, and then I'll just show that that's true. Sample 30, well, I'll just go to sample 33. So sample 33 is equal to 5.5 in column sepal length centimeters, and so that's true. And we did that for all of these samples as we went through. And then finally, argsort, which is also magic. So if we're going to sort this, letter A will be item 1 in the list, letter C will be item 3 in that sorted list, letter B will be item 2 in the sorted list, etc. So, cleaning exercises. I am not going to step through all of these, but I've got a series of cleaning exercises for you to do on your own. All the data you need is in the data folder. So if you want to, the path to your folder will be period, data, and then you should be able to auto-complete a lot of that stuff. So all your data will be in that folder, which you can do. And then go through all these exercises, do them, and don't peek. But if you're too lazy, you can just go to the solutions and go to the, and basically all the answers are written out for you. All you have to do is to execute them. So that brings an end to Python 201 cleaning data. Thanks so much for your time.